Topic 5, waves and the particle nature of light. This is about quantum physics, chapter 5.4. So you have already heard about Albert Einstein. Now when it comes to quantum physics, we have something called the Einstein's photoelectric equation. So his name would come into the minds of most of the students who are already familiar with quantum physics. And by the way, to answer the questions or to understand this chapter well, this is the math that you need. The electron volt, we will also see it, what is the electron volt and units of that, how to convert from electron volts to joules, joules to electron volts. You would have already learned that previously as well. Then the math that you need again, standard form is also called scientific notation. And then to convert it to ordinary form. We will see changing the subject of equation. You have already learned that in the O-level class also. Then very simple mathematics. So this is the math you need to answer or understand the topics in this chapter. And also you can see where this math is applied. It's indicated in the brackets here. Now let's start with chapter 5.4, part 1, wave particle duality. So you see wave particle duality. Dual means two. So we will see something to do with waves and particles, especially when it comes to the electron. The electron can behave as a wave and also as a particle. We will see the details. By the end of this section, you should be able to understand how the behavior of electromagnetic radiation can be described in terms of both waves and photons. So we are starting with electromagnetic radiation. So we will start with that. Like I mentioned earlier, electron also we can see, but first we will start with electromagnetic radiation. So how we can describe it in terms of both waves. Now you already know electromagnetic radiation is a wave. Electromagnetic waves we say. So how can it be described in terms of photons? We will see. By the way, the meaning of this word photon is important. And you can see the definitions of these words, like I have mentioned previously several times. At the end of each subchapter, the definitions are given. So here is the definition of a photon. Make sure you memorize this with the understanding, because in the exam paper they can ask you to write this definition down. Now if you can try to write it in your own words, but if you miss certain keywords, you may not get the full marks, especially when it's a definition. So best thing is to memorize with understanding, so that you have all the keywords that are necessary in the definition. Photons are packets of electromagnetic radiation energy where the amount of energy E is equal to hf, which is Planck's constant. Now this h is the Planck's constant and f is the frequency of the radiation. The quantum unit that is being considered when electromagnetic radiation is understood using a particle model. So here we have photons. So we have packets of energy. Then let's go back. Okay. So by the end of this section, you should be able to understand these two. And we will see how to use this equation for the energy of a photon of electromagnetic radiation. Okay, so let's basically go through this again. This is a very short part about the Huygens principle. The Dutch scientist Christian Huygens came up with the principle for predicting the future movement of waves if we know the current position of a wavefront. You have already learned what a wavefront is in the O-level class. The basic idea is to consider that any and every point on the wavefront is a new source of circular waves traveling forwards from the point. When the movement of these myriad circular waves is plotted, you can see that in the diagram here, and then their superposition is considered, the resultant wave will be the new position of the original wavefront. So here you can see. Now imagine this is you have these points here like this on this blue wavefront, and then from this you can draw these semicircles, taking this to be the center of the circle. You can do it with this like this, and then this here, which is touching the part of the circumference of those semicircles, will form the new wavefront. See, again, the basic idea is to consider that any and every point on the wavefront is a new source of circular waves traveling forwards from that point when the movement of these myriad circular waves is plotted, and then their superposition considered, the resultant wave will be the position of the original wavefront. So here you can see that you all would have learnt about interference of waves, diffraction. So even in the O-level classes you have learned that. Huygens construction for explaining the movement of waves. So here see original wavefront, new wavefront, secondary wavelets. Huygens geometrical system exactly explains all the basic phenomena we see light undergoing. We can make the drawings like figure A to correctly predict the movement of wavefronts in reflection, refraction, diffraction. So all waves undergo reflection, refraction, diffraction. You have learned that previously, and also interference and straight line propagation of light. And by the way, the arrows you can see can be considered to be rays. You would have learned that ray is always perpendicular to the wavefront. So these blue lines you see here are plane wavefronts, or they are parallel to each other. And these you can consider here, they are circular wavefronts. So always the ray is perpendicular to the wavefronts. In other words, it's at 90 degrees. It's normal 90 degrees perpendicular, all mean the same thing. Huygens construction correctly predicts diffraction through a gap. So you can see you can use this to predict the diffraction. Okay, so here you can see already light is a wave. We have seen numerous instances of light undergoing wave-like activities. Evidence that light is a wave. The interference pattern produced by diffraction and Young's two-slit, also called double-slit experiment, both require the superposition of wave displacements to generate the standing wave pattern seen. So when you learned about the Young's double-slit experiment, there was diffraction and also those diffracted waves. Remember, there were two slits. At each slit there was diffraction. When you learned the Young's double slit or two slit experiment, you saw that. Then these waves which underwent diffraction overlapped, or the correct word we can say superposition, because so that due to the interference. So then as a result it produced a pattern. Both require the superposition of wave displacements to generate the standing wave pattern seen. This is only possible if light is behaving as a wave and has the appropriate repeating cycles of displacements that cause this ongoing superposition to maintain the constructive and destructive interference that produced nodes and antinodes. Particles cannot superpose in this way. So that shows it is a wave. Now quickly I will show you the Young's double slit or Young's two slit experiment and what happens in this. We have learned this in the previous lessons also. So we have constructive interference, that is where you get a bright fringe like this, and destructive interference where you get a dark fringe. So remember, there were alternative dark and bright fringes. Let's have a look at that quickly to quickly review what you have learned. Alright, so here you can see the double slit. Now what happens is the monochromatic light is coming like this from the laser. Then there are two slits. So what happens is at each slit there is diffraction, similar to this you see here. In the case of water waves, there are plane wavefronts or parallel wavefronts coming this way. Then here there is a aperture, hole or slit, gap, and there is another gap here. So what happens, you can see diffraction occurs, and on this, at this gap also there is diffraction. Now what happens, these diffracted waves interfere on this side, and as a result you have constructive interference and destructive interference. Same thing happens here. Where there is constructive interference, you have a bright spot, also called a bright fringe. Where there is destructive interference, you have a dark spot or no light, also called dark fringe. So how this happens, we have learnt it in the other lessons. Okay, so let's go back to what we were doing. So I wanted to show you the diffraction and interference. Let's go back. Yeah, so we are back here now. Yeah, so that was the Young's double slit experiment. Now, that is also very important in the exam papers. They can ask you about that as well. All right, this is only possible if, okay, we went through this. This is only possible if light is behaving as a wave that has appropriate repeating cycles of displacement that cause this ongoing superposition to maintain the constructive and destructive interference. So when superposition happens, that is when, let's say, the crest and the trough come together, there is destructive interference at that point. If the crest and crest or trough and trough come together, we have constructive interference. So constructive interference produces the bright fringe, destructive interference produces a dark spot or a dark fringe. Okay, this ongoing superposition to maintain the constructive and destructive interference that produces nodes and antinodes. So when it came to standing waves, you saw the nodes and the antinodes. So that's another lesson. Particles cannot superpose in this way. Now you can see superposition effects such as standing wave pattern are only possible if light behaves as a wave. Okay, so polarization, that is another topic, is another phenomena exhibited by electromagnetic waves, including light, that can only be explained in classical physics by using the ideas of waves. Okay, so now we will see how light can behave as a particle, because this is what we will need for the next part, where we will apply the Einstein's photoelectric equation. In some cases, the examples of light acting as a wave are phenomena that can only occur for waves in section 5.4 part 2. So this is 5.4 part 1. We will see the details in 5.4 part 2. We will need to apply this there, where we will see photons, where light is acting as a particle, because one photon removes one electron. So we will see that in the next part in section 5.4.2. Right now we are in section 5.4.1. We will look in detail at the photoelectric effect. This was first observed in 1887 by Heinrich Hertz, after whom the unit for frequency is named. So the unit of frequency is Hertz. It's named after this person, but it was not until the beginning of the 20th century that an adequate explanation of phenomena was made. So this is just for additional information. I am going through the history. Working on the basis of Max Planck's 1901 suggestion that light could exist as quantized packets of energy called photons. So it's like fixed amounts of energy. Like I said, one photon removes one electron. Later you will see when it comes to the Einstein's photoelectric equation. When ultraviolet falls on a metal surface, it removes electrons from that metal surface. So one photon removes one electron. Einstein produced a paper called in English concerning the heuristic point of view towards emission and transformation of light. Einstein wrote 4 important papers in 1905. Again, this is additional information. We can go through it quickly, including one on relativity and one regarding E equals mc squared. You have learned this equation already. You have seen it, maybe even if you didn't learn physics before that also, you would have seen this. But it was the explanation of the photoelectric effect for which he was awarded the 1921 Nobel Prize in Physics. Crucially, the photoelectric effect cannot be explained using a wave theory for light. However, the idea that light travels as particles, or photons, particles or photons, whose energy is proportional to the frequency, it would have when considered as a wave. So that's why we will see the equation E equals hf. Energy of photon is h, the Planck's constant, times f, the frequency. We will see that. However, the idea that light travels as particles or photons whose energy is proportional to the frequency, it would have when considered as a wave, fits all the observations exactly. Okay, so here this is the very important equation. So in this lesson, these are the important points. E equals hf, quantization, photon. Again, all these are given summarized here, so it will be easy for you. So the main equation is this one. Okay, let's see. Photon energy. For electromagnetic radiation, the energy of the photon can be calculated by multiplying the frequency by the Planck's constant. See, photon energy is equal to the Planck's constant times the frequency. So E equals hf. E is the photon energy, h is the Planck's constant, f is the frequency. Now energy, you know, has the unit joules. Frequency has the unit hertz. Hertz is what? Number of cycles per second. So it's actually per second. That's how we get the unit of this. So if you make h the subject of the equation, h is equal to E over f, and the unit of h will be joules per second, joule second, because this is per second. So when you write the unit on this side, joules divided by per second is joule second. So the unit of the Planck's constant is joule second. This constant has an extremely small value because it represents the fundamental minimum possible step in energy. In SI units, H is equal to 6.63 into 10 to the power minus 34 joules. This is also given in your data sheet. So no need to memorize these values, but when you do a lot of questions, you will automatically memorize it. If we work on very small scales, photons cannot have energy values that differ by less than the Planck constant. This means that there are some energy values that are impossible in our universe. Such a system of minimum size steps is called quantization. So now you know what quantization is. So it can have certain fixed values of energy. So we will see. So it can only be multiples of those numbers that are possible for the amounts of energies of photons. So this way we will see now how understand this better. So quantization. Now if you go to the bottom here, that is the last part of this subchapter 5.2.1, you can see what quantization is the concept that there is a minimum smallest amount by which a quantity can change. Infinitesimal changes are not permitted in a quantum universe. The quantization of a quantity is analogous to the idea of the precision of an instrument measuring it. So you know the precision of an instrument is the smallest division in the instrument. So for example, if you consider a ruler, the smallest division in the ruler is a millimeter. So you have 1 millimeter, 2 millimeters, 3 millimeters, maybe the ruler is 15 centimeters. And so we have 150 millimeters. So you can see the smallest division is 1 millimeter. Think of it like that. There is a smallest amount of energy. Okay, let's see now. When we do this, you will understand this better. Okay, so this means that there are some energy values that are impossible in our universe. So if you look at the ruler, the smallest division is 1 millimeter. So it has to be a whole number of millimeters. You can't have in a ruler 1.5 millimeter division. If it's calibrated with the smallest division, which we call the degree of precision to be 1 millimeter, it should be the 1 millimeter, 2 millimeters, 7 millimeters, a whole number of millimeters. So you can't have 7.3 millimeters on a ruler. It's something like that. Okay, so let's use this equation now. This is a very important equation. You should know it. Calculate the energy of a photon of yellow light that has a wavelength of 550 nanometers. So very simple. Let's do it now. Now for this equation, you know that wave equation V equals F lambda. And when it comes to electromagnetic waves, since they travel at the speed of light in vacuum, we can replace the V with a C. So we have C equals F lambda. Now if you make F the subject of the equation, it will be C over lambda. So if you want, you can substitute that here, then you get E equals HC over lambda, E equals HC over lambda, and that can be used to solve this problem. Otherwise, you can find F first. Using this second equation, you can find what the frequency is and substitute that in the first equation here to find the energy of a photon of yellow light. So we know the wavelength. If you want, you can write E equals HC over lambda and do it, or you can find F first and then substitute for F here and get the value. So that's what they are doing. They are first finding F and then they are finding the energy of a photon of yellow light. So we see photon of yellow light. Calculate the frequency of gamma ray photon that has 2.24 into 10 to the power minus 14 joules of energy. Now the energy of the photon is given. You have to find the frequency. So very simple. E is given, that is 2.24 into 10 to the power minus 14. You can substitute that. H, that's the Planck's constant. It will be given to you in the data sheet, and then you can find the frequency of that gamma ray photon. So very simple. Now we will see electrons as particles. So you see, previously we saw electromagnetic radiation as a wave, and also we explained it as a particle by saying about the photons and quantization. Now we will see electrons as particles. Experiments that produced ions can demonstrate electrons behaving as particles because a fixed lump of mass and charge is removed from the atom in order to change the atom into an ion. So that's very clear. You are removing something that has a mass and also a charge. So therefore we can say it's a particle. So electron is a particle. The charge to mass ratio is a uniquely identified property of particles and was first demonstrated for the electron by J.J. Thomson in 1897. In the O-level class you would have learned about the discovery of the electron and then J.J. Thomson's plum pudding model and all that. He discovered the who discovered the electron. Robert Millikan, in an experiment finally published in 1913, took this one step further to find the electron charge itself. Again, this you can take it as additional information, the history, the fact that electrons hold a fixed amount of charge. So you know the elementary charge is 1.6 into 10 to the power minus 19 coulombs. So if it's 1 electron, it has that value negative. If it's 2 electrons, 2 times that value. So you see that amount is also a fixed amount. So you can't have quarter of that when it comes to an electron or a proton. It has to be either 2 times the charge of electron, 3 times if you consider, let's say, a certain number of electrons. If you have 5 electrons, it will be 5 times the elementary charge, 5 times the charge of an electron. The fact that electrons hold a fixed amount of charge and a fixed mass indicate that they are localized particles. So you know the electron has a certain mass, it also has a certain charge. Okay, so again this you would have seen in the O-level class, but this is just for additional information. You can go through this. Robert Millikan's oil drop apparatus showed that electrons have a fixed charge of 1.5924 into 10 to the power minus 19 coulombs. So this is what we approximate as 1.6 into 10 to the power minus 19 coulombs. The difference with the currently accepted value is caused by a mistake in Millikan's calculations because he used a slightly incorrect value for the viscosity of air. So anyway, we take it as 1.6. Okay, so now we saw electrons as particles. Now we will see electrons as waves. If electrons are made to travel at very high speeds, they will pass through gaps and produce a diffraction pattern. So if it can diffract, then it should be a wave. You know, waves undergo reflection, refraction, diffraction, and also they undergo interference. So we will see now. So here you can see the electron undergoes or produces a diffraction pattern. They will similarly interact with a double slit apparatus to produce the interference pattern seen when waves pass through 2 slits. Diffraction and interference are not expected by classical particles, as they should simply travel straight through the slits. Observation of these experimental results proves that electrons can behave as waves. So we will see waves or particles. So now this is what we have to show that electron can behave as a wave. It can undergo diffraction and it can show diffraction and interference pattern, which is seen by the waves. When we studied the Young's double slit experiment, we saw that. So waves or particles. So that's how we come across this wave-particle duality. Now we will see this. The experimental observations highlighted in this section have suggested that both electrons and electromagnetic radiation seem to contradict our explanations of them. Physicists have good theoretical descriptions of the wave and particle nature for electrons and also for electromagnetic radiation. So for electrons and electromagnetic radiation. However, we do not have a complete and perfect single theory that explains both correctly for either electrons or electromagnetic radiation. So this is the evidence we have, but we do not have a perfect single theory that explains both correctly. Maybe in the future they will explain it correctly. So for now we will have to learn what we have learned here based on this. So phenomenon, light, electron. So for example, light, evidence of waves here, evidence of particles. What is the evidence that light is a wave? It's very simple. Diffraction, interference, and also they can undergo polarization. Waves can also undergo polarization. Then evidence for particles is the photoelectric effect. Like I said, later we will see how this photon removes one electron when it comes to the photoelectric effect. Then electron, evidence for waves, diffraction and interference. Then evidence for particle, ionization. You can remove the electron from an atom and the atom becomes an ion. So that is ionization. Summary of the evidence for light and electrons behaving as waves or particles. The idea that these things behave as waves under certain circumstances and as particles under other circumstances is known as wave-particle duality. So now you know that. Okay, so you can answer these questions and check the answers in the answer script. That will ensure that you understood this theory well. Alright, so here are the definitions. Like I said, after every subchapter there are some definitions which will make it easy for you. So we went through these two, photons, quantization. Let's go through this bit. Wave-particle duality is the principle that the behavior of electromagnetic radiation can be described in terms of both waves and photons. So these definitions are important. Make sure you study them. Next we will see the photoelectric effect.